In today's class, we'll be looking at some ideas from Chapter 5, Sections 5.4, 5.5, and 5.6. 5.4, we look at enthalpy changes as they're connected to a reaction. In 5.5, aspects of calorimetry, which involve calculations with heat capacity and specific heat, and seeing how they pertain to experiments. And then finally, Hess's law, where we're using enthalpy as a state function to combine different reactions to result in a target one that we're looking for. All three of these sections, 5.4, 5.5, and 5.6, typically show up as exam questions. So we need to master skills from all three parts. 5.4, looking at the enthalpy change for a reaction. The enthalpy change, that's given that symbol delta H. First thing we want to remember is that enthalpy is an extensive property. It depends on the amount of matter that's there. If you change the amount of matter, you change the enthalpy change. So in this case, notice how the coefficients have all been multiplied by 10. 10 times as much matter involved, the change in enthalpy is 10 times as much. Second, reversing a reaction is going to change the sign for the enthalpy change. If we are looking at the reaction H2 plus O2 to give H2O, if we switch that around, we'll still have the same magnitude for the enthalpy change, but the sign changes. Those are two ideas that we want to be able to apply. In the pre-class activity, we had this table to fill in. We had a balanced chemical equation, and it says the coefficients in the equation are the mole amounts. When you have 2 moles of hydrogen gas reacting with 1 mole of oxygen gas, it would produce 483 kilojoules of heat. Produces it, that's what that negative sign tells me. How much heat would be produced in these other scenarios? Second one right there, if all of the mole amounts are twice as much, then the change in enthalpy is twice as much. Take a second, see if you can work with your classmate. Compare your work for the next 2 boxes. What I see in the third box over, the coefficients are half as much as what was provided with the balanced chemical equation. So the enthalpy change, the amount of heat produced, would be half as much. The last one, a little bit tricky within that, because in this case, we had a limiting reactant, which was a hydrogen gas, 1 mole of that, and the O2, that was in excess. So the coefficient that was really important was the one that we had corresponding to the limiting reactant. So what we're beginning to see is how enthalpy changes could be linked to balanced equations, which means they can be linked to stoichiometry. Conceptually, if you have an explosion here of hydrogen and oxygen gas to produce H2O, where's that energy coming from? So to think about this conceptually, we could begin with the hydrogen gas and the oxygen gas as molecules. We would have to break them apart in order to get the particular atoms. Now, breaking a bond is always going to take energy. Breaking a bond is always endothermic. And yet the overall process here is exothermic. Why? Because we have the coming together to form the new bonds. Bond formation is always exothermic. So conceptually, even if we have an endothermic component, if the bond formation is more exothermic than it was endothermic, the net change in this, comparing the final minus initial, ends up being exothermic. Section 5.5, this involves calculations that include heat capacity, specific heat, and then specific types of experiments. So this first one, what is the heat capacity? It's the amount of energy required to change the temperature by 1 degree. 1 degree Kelvin, 1 degree Celsius, doesn't matter because the size of the degree is the same in either of those scales. The units for heat capacity, joules per Kelvin. You add a certain amount of heat, and given that scaling factor, the heat capacity, you can see how much the temperature changes. Now, if you're looking at a pure substance, the heat capacity is usually given for the amount of substance that was involved. The molar heat capacity, that's what that symbol corresponds to, is an example. We'll often see the heat capacity in units of joules per gram K. That's our specific heat. So it's similar to the heat capacity, but when we have it per gram, then it's referred to as the specific heat. Not a huge distinction for us, but we just have to be careful with our units. Are we looking at joules per gram or joules per gram K? More often, we'll be using joules per gram K, the specific heat. So if we have a certain amount of heat, we consider the specific heat value, the mass that's involved, and how that changes the temperature. This table has some specific heat data for us. If we look at them, we find that some of them have larger values, some of them have smaller values. H2O liquid, that's one of the larger values listed there. A larger value is telling me that the temperature of that substance does not change as easily when heat is being added. To change the temperature, more heat would be required. So here's just an illustration of that. Let's say we had 125 joules of heat and it was added to 50 grams of aluminum, or 1,275 joules of heat being added to 50 grams of water. So in both of these cases, the same amount of heat's being added to 50 grams of a substance, but the substance was different. If I wanted to calculate the change there for the aluminum, I would use this expression where the heat being added is equal to the specific heat, the mass, and the change in temperature. I have the heat added, the specific heat from the table, 0.90. 50 grams was involved, so it would change the temperature by 28.3 degrees. To do the same with water, everything's the same except we have a different specific heat value. Because it is larger, the change in temperature is less. Experiments involving heat capacity, specific heat, ideas like that. Here's an example, okay? This is one that's taking place in what's called a calorimeter. Now, you could have basic calorimeters, like just some styrofoam cups in order to have it insulated, or more advanced ones. In a lab, you're going to end up exploring the ones using a coffee cup. So within here, we have an acid and a base in a neutralization reaction. We might see enthalpy data reported for it. How do they get that data? First thing we want to note, let's say we mix together the two reactants and the temperature goes up. First thing we want to note with that is exothermic. If the temperature increases, it's an exothermic process. Heat will now leave the system. Let's get that in our heads and get that straight first of all. What if then the opposite takes place? What if you mix the reactants together and the temperature goes down? In that case, it would be endothermic. Heat will now have to enter the system to return it to room temperature. So by looking at the thermometer, it tells us whether it's exothermic or endothermic. Here's an example from the end of chapter, and this steps us through a good procedure to be able to answer questions like this. So we have a scenario. 6.5 grams of sodium hydroxide was dissolved in 100 grams of water. It took place in this coffee cup, and the temperature goes up. So let's step through the different parts of the question. Is the process exothermic or endothermic? That will allow us to determine what the sign will be for the change of the heat. For that, we can just look at the thermometer. I see that the temperature increases from 21.6 to 37.8. Temperature goes up, that's exothermic. So when we report our answer at the end, we want to have a negative sign. How about the amount of heat that's involved? We can use our expression involving the specific heat, the mass, and the change in temperature to determine Q. And to do that, we have to look through a few of the different details. So it says within here, use a specific heat of 4.18. So we'll use that in the expression. We need a change in temperature. Well, we know how much it increased, so let's use a change in temperature, 16.2 degrees. What changed temperature? Well, it was that entire aqueous solution. It was the sodium hydroxide that then dissolved to give us, in the reaction, H2O and NaCl aqueous. So the entire mass of the solution, we use both of those parts. That's where I'm getting 100 and the 6.5 added together to give me 106.5. If we put all of those in the expression, we could figure out how many joules was involved and report it also as kilojoules. Final step. How do we report the information? It wants it reported as the enthalpy change per mole. The enthalpy change in kilojoules per mole of the sodium hydroxide. So we now know how much heat was involved. Let's figure out how many moles were involved. So I'm simply using the molecular weight to figure out how many moles were involved for the sodium hydroxide, and we'll report it that way. Certain amount of kilojoules per mole. And at this point, I just want to say I need to have a negative sign on that. I know that it's exothermic by looking at the thermometer at the start, and at the end of the process, I make sure my answer then is negative. Now, there was a lot going on within this one. 3 parts to go through. What questions do you have on this? What parts of this remain confusing for you? Moving on to our third topic, our third skill. So this is an application of what's called Hess's law. This is an application in which enthalpy, because it's a state function, the pathway that we take from going from between our initial and final states, the pathway itself doesn't matter. The overall enthalpy change will be the same if we consider our final minus initial. The pathway that we have going between those two doesn't matter. That's being illustrated here where it's pointing out that you could take a reaction and follow this blue line and go straight from these reactants to these products. Or you could do it in 2 steps. You could do it in this green and then the next green. Adding those together, it also equals the enthalpy change that's shown here in blue. Now that might seem like an abstract idea. Let's look at what that means. This is taking advantage of the fact that enthalpy is an extensive property, and that the enthalpy change for a reaction, remember, if we write it in reverse, the sign will change, but we keep the magnitude the same. We're going to apply both of those and connect it to enthalpy being a state function. So first, let's practice those first 2 parts. Let's say we had this reaction, A plus 2B to give me AB2, and we have an enthalpy change of minus 200 kilojoules when these are the coefficients as written. So if we were to vary those coefficients, we would vary the delta H because enthalpy is an extensive property. So if we were to triple all the coefficients, the enthalpy change would be tripled. Take a second, fill in the other boxes. Check your work. If you were to have all the coefficients cut in half, what would be the enthalpy change? What if you reverse the reaction? What if you reverse the reaction and change the coefficients? Take a second, work on that. Here would be the different answers. So if we took all the coefficients and cut them in half, instead of minus 200 kilojoules, it would be minus 100. In this case, we've reversed the reaction. So instead of having negative, it's positive. And in this case, we've reversed it and cut the coefficients in half. We want to be able to do manipulations like these. Consider this reaction. So if we have a combustion reaction beginning with methane, the first step as I'm conceptualizing what happens, I would have to have the bonds broken, breaking apart the molecules, and then the formation in this case ends up being exothermic. So here's that particular reaction as written. Now, what if instead of having the product be H2O gas, I wanted it to be H2O liquid? So I could consider what does it take to have the reaction go for an enthalpy change to first reach H2O gas and then continue on to reach H2O liquid. How might I get that? Well, I don't necessarily need to do that experiment. I know the data for the first one. If I then combine that with data of going from H2O gas to H2O liquid, I can now just combine both of those to get the overall enthalpy change. That's what Hess's law has us do. So if we were to take those and add it all together, I've added together all the reactants from these 2 experiments, all of the products from these 2. As I look at that, I see I have some terms that I can cancel that were then the same on both sides. After having canceled, it leads me to the net desired equation. If I'm simply adding together the reactions, I add together the enthalpy values to get the overall change. Let's see another one and sort of think about the strategy we could use to solve this. So in a Hess's law problem, we have a target reaction listed like this. We want to determine its enthalpy change from provided data. So we're going to manipulate the provided data so it matches up to what the target expression is. So my strategy for this, I look within the provided equation, C2H2 gas. Where is that listed amongst the different provided reactions? It's only listed in this first one as a term here. So I'm going to use that expression. I'm going to use that expression and make it so I have C2H2 written as a product. Right here it's written as a reactant. So what I'd like you to do, write the reverse of this reaction right here. Write the reverse of it, including the delta H. Next one, when it comes to the carbon, carbon is listed as a reactant with a coefficient of 2. In this expression right here, I see carbon as a reactant, but it's not a coefficient of 2. So let's write this expression with all of the coefficients doubled and the delta H doubled. Third part, I need H2 as a reactant with a coefficient of 1. Okay, perfect. That's what's provided right here. H2 as a reactant with a coefficient of 1, so we can just write that reaction unchanged. And here would be what we could then cancel. The first reaction we've reversed, and the sign of the delta H was changed. The second one, we doubled all the coefficients, and so the delta H changed twice as much. The third one, we could write just as is. If we add them all together and cancel, we can see that we get the targeted reaction. So then we simply add together the delta H values, and that's the enthalpy change for our target reaction. So in this overview, we looked at 3 specific skills: enthalpies of reaction, calorimetry experiments, and Hess's law. And in class, you're going to have an opportunity to practice all 3 of these.